it is my pleasure to introduce our second keynote speaker, Professor Iqbal Mujtaba from the University of Bradford, United Kingdom. Before that, allow me to share a little bit about Prof. Mujtaba. He is a professor of computational process engineering and is currently Associate Dean, Learning, Teaching and Quality of the Faculty of Engineering and Informatics at the University of Bradford. He is a fellow of the Royal Academy of Engineering, fellow of the IChemE, a chartered chemical engineer. He was the chair of the European Committee for the Computers in Chemical Engineering Education from 2010 to 2013, and the chair of the IChemE Computer Aided Process Engineering Special Interest Group from 2012 and 2019. Professor Mujtaba leads research into dynamic modeling, simulation, optimization, and control of batch and continuous chemical processes with specific interest in distillation, industrial reactor, desalination, wastewater treatment, and crude oil hydrotreating for focusing on energy and water. He has managed several research collaboration and consultancy projects with industries and academic institutions in the UK, Italy, Malaysia, and global. He has published over 400 technical papers and has delivered more than 80 invited lectures, keynotes, short courses around the world. He has supervised 43 PhD students to completion and is currently supervising 9 PhD students. Professor Mujtaba is the co-author of few textbooks such as Batch Distillation, Design and Operation, published by Imperial College Press, London, Wastewater Treatment by Reverse Osmosis, published by CRC Press, and Desalination Technologies, Design and Operation, published by Elsevier. He is one of the co-editors of the books such as The Water, Food and Energy Nexus and Waste Management, Social and Technological Perspective, published by CRC Press. Today, Prof will share his keynote speech entitled "To Control or Not to Control? That is the question, why and how." Please join me in welcoming Professor Iqbal Mujtaba.
Thank you. Thank you very much. Good morning, everyone. Can you hear me?
Yes, I can hear you, Prof. Okay. But anyway, I cannot see your face.
Yeah. Let me share that and then see whether it works or not.
Okay.
Can you see the slides now?
Yes, I can see the slide now.
Okay, good. So let's put it in a full mode, presentation mode. Can you see now? Is that okay?
Yes, Prof. Yeah, Prof.
Okay, good. Thank you. Right. Okay. If you at any point, if you cannot hear me, just let me know. So, good morning, everyone from UK, and of course, good evening and good afternoon from Malaysia. Right. So, as you can see, the title of the talk today, "To Control or Not to Control," that is the question, why and how. And I'd like to start with thanking the organizer to invite me to this interesting conference. And control, let's have a look at a couple of examples before I share with you what we have been doing over the years in that. So let's see if we can move to the next slide. Let's move to the next slide and tell me that whether you can see it or not.
Okay, sure, Prof.
Can you see this slide now?
Yes, Prof. Yeah, okay. It's visible at my end.
Visible. Okay, I hope the other audience can see. So what I wanted to start with to see what this process control has got a relevance to our society, right? So as a society, what we want is in the green box, as you can see here, that we want. That is like our set point. That is our desired target kind of thing in the control term. So you'd like to have a smart, resilient, cohesive society, right? Where we have got zero pollution in air, water, soil, etc. And we want to live our life comfortably. That's what we want. That is our target. That's our set point. So what you need to have to achieve that set point, you need to have a sustainable supply of water, food, energy, and of course you need a fair amount of education to educate the society. Now what happened in the society, like in any processes, you always have external disturbances. So in the society also we have got disturbances like war. We have got pandemics. We just had pandemics a couple of years ago. We have got disaster like natural disaster, man-made like tsunami, etc. We have got earthquake, and we have got EDI non-compliant behavior. What we mean by EDI is equality, diversity, and inclusion. We are very selfish sometimes, and we don't care about other people, their feelings, their religion, their race, and etc. So all these are disturbances, external disturbances. And what does it do to our process or to our society? The impact is a climate change, pollution. You have got air, water, soil pollution, water scarcity, food security, energy security, displacement of people from one country to another country, flood, and of course, then completely EDI non-compliant society we come up with. So then you need to have a control action. Some action is needed to bring the society back to where we want, like the set point, right? So you need to have some actions like a short-term, medium-term, long-term action. And as we all know, the climate change, population growth, and geopolitical instability impact water, energy, food resources, which are critical to communities' livelihoods and health and well-being. So this more or less, you can see the process control has got a similarity with what we see in the society. Another, personal level kind of process control we see almost every day if you are in a cold country, but I'm not sure. Malaysia is very hot. Whether you also have a hot shower, I'm not sure whether you always have a cold shower. But in the West, where it is the cold country, we see the process control almost on a daily basis when you want to have a shower. So it's like a feedback control system. So you have got the process, like you have got the water supply and the human being having a shower. And then, of course, your brain sense whether your water is too cold or too hot. And then you take that and then you take a control action. So your brain works as a controller and then decides that, okay, either the hot water tap needs to be manipulated or the cold water tap needs to be manipulated. So you do some kind of manipulation and get it back to your desired temperature, what you want for your shower. So some people like very hot shower, some people like a mild hot. So of course that control system is different for different people, even though using the same shower room. And it's a typical example of a feedback control system. So if we look at the next one, the process control analogy with the societal control. So what is the process control? So I'm not spending too much of my time today. I'm sure this is the control conference, everybody knows about it. But of course, the process control is the ability to monitor and change the process subject to any disturbance, as I mentioned. And it involves the consistent and continuous monitoring of the process like we do in a shower. You need to have it. You cannot just stand under the very hot water for a long time. You monitor it, you sense it, and you take the control action. So a typical controller, I'm sure in the last many presentations, you have seen this diagram probably again and again. So you have got a process, the process gives you the state, and of course you have got a set point, and then you take the control action, and etc. And often you have got disturbances, as I have mentioned, the disturbance coming from outside. Sometimes the valve may fail, and then you may not have the steam flow at you want, or the water flow rate as you want. So these are all disturbances, valve failure, and many other actions. But you need to operate your process in a way that you make the product on the right specification. So our ultimate goal in any manufacturing process is to produce product on spec, because that's what earns our revenue. We cannot compromise with the product quality and let it go and let a process run uncontrolled way. Then what will happen? We will be producing a lot of products which will not meet the specifications. And of course, if it does not meet the specification, you will not be able to earn the revenue. So process control is very, very important from the business point of view, from productivity point of view, and et cetera, et cetera. So again, I'm sure we don't have to go through in detail, but of course, any process control, you have to have a controlled or measured variable, the variable you want to measure, and then of course you manipulate something, and then you get a set point you want to achieve that set point, and you track that set point and take control action. So in terms of a manufacturing process or chemical engineering process, for example, you need to find out the optimum temperature of a reactor, for example, and because you want to maximize the conversion, or you want to achieve some product with the minimum time kind of thing. So knowing the optimum parameters for your process is very, very important. And sometimes these are obtained by trial and error, and sometimes by using model-based optimization system, that where you optimize the process and you know exactly what temperature you would like to have in a reactor to operate. So getting the set point a priori before applying your control system is very, very important. And how you achieve it, that's a different topic. But I'll go through some of the examples here today before we talk about the different types of controllers we have been using over the years. So why process control? As I have mentioned, why process control is very, very important from the point of business, from the point of profitability, from the point of maintaining the quality of the product. It is very, very important. And we have to have control in our personal life as well. For example, you earn money and then you spend money. You have to have a proper control in your spending. Otherwise, you will not have enough money to run your family or whatever it is. So control is a part of our life, our personal life, our societal life, and of course, the manufacturing process, certainly. So if you look at some of the examples we have been working on for some times, this is a jacketed batch reactor here, where A is reacting to produce B, and B is producing to react C, and B is our desired product, for example. And say, for example, we would like to maximize the conversion of A to B, our desired product, in a fixed batch time. Why it is a fixed batch time? Because maybe this desired product is required in a downstream process, and the time you cannot just play with. You cannot have infinite amount of time to just maximize your amount of product. You may have a given window within which you have to produce B and supply to the next process. So there is a problem we are trying to achieve, that we applied the offline optimization to find out what is the optimum reactor temperature within that 3.5 hours of batch time, and then which will maximize the conversion to B. And this simple example, it was a part of the PhD research with my student, and that student was from Malaysia, who is a professor at USM at some point. I think he has taken early retirement. So that was 2001 when he was trying to do some offline optimization and then online control as well. So you can see the reactor needs to be operated at about 369 degrees centigrade within that 3.5 hours of batch time to maximize the concentration of B or conversion to B. Next example, again, a different types of reaction. As you can see here, A plus B is producing C, and then A plus C also reacting to produce D, and the C is the desired product here. So of course, if the reactor is not carefully controlled, you end up with producing a lot of D, and obviously that is not wanted. So in this particular example, again, offline dynamic optimization problem, either you can have one window within which you apply the temperature control. For example, the first run one, you can have a just single temperature there, 92.4 degree centigrade within 2 hours time 1 to 120 minutes, and you maximize the amount of your component C, and or you can have a 3 sort of interval, and in each interval you have got optimum temperature. For example, the second run, for the first 40 minutes you have got about 93 degrees centigrade. Then in the second 40 minutes you have got about 91 degrees centigrade. Then in the third interval you have got again 93 degrees centigrade. Again, these are model-based optimization. I have not shown all the mathematical equation goes behind it, the model of the reactor, the detailed model, etc., because I don't think we'll have time. And I hate to present mathematical equations in conference presentation, because that's not at all an important as far as this presentation is concerned. So you can see that in this particular reactor, we optimize the temperature offline. We find out what are the optimum temperature. Then, of course, we can apply the controllers. We can design the controller to track this temperature, and we'll talk about this at a later step. Another example here, the polymerization reactor here, which is the, again, you can see the initiation step in polymerization, then you have got the propagation step, then of course you have got the termination step. These are basic 3 steps in polymerization. There may be more steps there. So optimal control problem, the offline, because you want to determine the temperature of the reactor, and of course you want to know the initiator concentration as well, you want to optimize, and then you want to minimize the batch time. Here it's interesting that you want to make a product, but you want to minimize the batch time for the polymerization. That helps when you want to run multiple batches of products and you want to achieve a certain target of your product, that amount you have to produce, and then minimization time will maximize the number of batches of products you can produce. Again, the objective function of the control depends on your business. Sometimes you may have a fixed time window, as in the previous example. Here, we are trying to minimize the batch time. Of course, we want to obtain a certain amount of conversion, monomer conversion, and we want to have a number average chain length which is given. So the next slide will give you the results of that offline optimization. As you can see here, there are 3 intervals here. The minimum batch time is a 3046 second, and you can see in every interval the temperature which needs to be tracked to get exactly monomer conversion of 30% and chain average length of 500. And in it, the optimum initiator concentration would be 0.888. So this is a styrene polymerization, which was carried out by our PhD student Emmanuel Ekpo back in 2006-07. He completed his PhD. But this example was also followed by another PhD student from Malaysia. She's at UPM. At the moment, she's, I think by now she is a senior lecturer, most probably. And that's about the styrene polymerization. Next example here is again a free radical polymerization, but for a different, of course, monomer. Again, you can see the polymerization steps. It has got initiation, propagation, termination, and the chain transfer as well. So when you look at the optimal control problem and you want to find out the offline optimum parameters, which you can then use as a set point for your controller, that was what we are trying to do. So for this particular methyl methacrylate polymerization, as you can see here, again, we wanted to minimize the batch time, but then again, our target was the molecular weight. Of course, the average molecular weight of the polymer we want to produce is 150,000 on the left-hand side, as you can see here. And on the right-hand side, you can see the temperature that needs to be tracked in different intervals of time. And of course, the final batch time, which is the minimum, is at 2966 seconds. And that paper was published in a neurocomputing several years back. So this and again, another example where you need to apply process control to track the temperature. Next example here, again, the milk pasteurization process. Milk is very essential for all of us. The milk pasteurization process requires the heating of your milk at a certain temperature and holding it for some time, and then you need to cool it down. So you heat it up to 76 degrees centigrade in a holding tube. Then you cool it down to 3 degrees centigrade. That's the pasteurization process to kill all the microorganisms. And then, of course, the boiler temperature to heat up which produces steam is kept at 92 degrees centigrade. And the ripple plate where you run through ice, cold ice to cool down the milk, set at 2 degrees centigrade. This work was carried out with a PhD student, Satit, and he was in Chulalongkorn University, Malaysia. So we have done it a couple of years ago. And we applied, again, the control system to control this temperature or the set point. So this is another example. The next example is a desalination process. You know, the world is short of fresh water, and a lot of desalination processes are around the world. I'm not sure about Malaysia, how much desalination process you have got. Maybe you have got a lot of water treatment and membrane-based water treatment process. I'm not sure about desalination. So in the Gulf areas and the Middle East and many other countries, in islands especially, for example, some of the Spanish islands, Cyprus, etc., they have got shortage of water, but they have got plenty of seawater. So they desalinate that water and to get this fresh water. So how does it work, the process? Maybe for some of you, you have got the seawater coming on the right-hand side where it is showing the can you see my mouse moving?
Yes, Prof.
Okay, fine. So this is the seawater where it gets into the process here and is being preheated again. And then, of course, part of this preheated seawater, you can see here, is rejected back into the water to meet up the thermodynamic requirement, because the second law of thermodynamics required that flushing off some of the liquid, the seawater back into the sea. And then, of course, this heated seawater goes through the recovery section here, is being heated up, and then finally it gets to further heated up by brine heater here, where steam is supplied, and you get the highest temperature of the first stage of the process. And so the seawater right at the bottom of the first stage, enter into the first stage, is being flushed and vaporized, and you produce the fresh water, which is being condensed in this middle trace here. All the way you can see the fresh water is being produced. And then the heat of vaporization or the heat of condensation is being used to heat up the preheat the seawater temperature. Now, what the problem is in here, that if you have got a fixed configuration, the fixed plant design, and you do not change any of the operating parameters, so what will happen? The seawater is continuously changing. So winter time, when the seawater is less, you produce more water, but when it's summer, the seawater is hot, you produce less amount of water. Look at the fresh water kilogram per hour. So you can see you have got a significant drop in the production of water from winter to summer. But in reality, what happened, if you look at the demand and supply, winter you will need less water, and of course, in the summertime, you need more water because you use gardening water, you have more showers, and etc., etc. But if you do not do anything in the process, what will happen in winter time? It will produce more water, and summertime less water, and it is not desirable by any company, anybody producing this water, because it's not meeting the demand of the client. So they have to do something. So what they do, even to produce the fixed amount of water, the temperature here, which is called the top brine temperature after the brine heater, that temperature in winter is lower than in summer. The summer, they have to operate at a very high temperature here, 115 degrees centigrade, and summertime, they can operate about 90 degrees. So the problem it creates is that you end up with a lot of heat exchanger fouling in all the way, the heat exchanger fouling, as you can see in the picture. And that heat exchanger fouling creates another problem, that you have to stop the process often to clean and maintain the heat exchanger. And that is, again, not desirable in that respect. So what we have been doing through offline optimization, we are looking at the winter to summer conditions here, and we are trying to optimize offline the number of stages you need, and the top brine temperature, the temperature which goes to the first stage of the process, we almost fixed it to 90 degrees because we don't want any fouling of the heat exchanger by operating at higher temperature. So we are looking at that one for a fixed water demand of 700,000 kilogram per hour. And that work was quite interesting. That solves quite a lot of problem. That yes, if you design your process in a summer condition, then in winter condition, you don't need all the stages. You can only use some of the stages, and some of the stages can be freed to maintain for your heat exchanger. So you don't have to shut down the plant, and then you can optimally operate it. But again, to operate the desalination plant with a top brine temperature of 90 degrees, that requires a control action. How do you maintain that temperature? How do you control? How do you track? That is the process control, the control aspect of that, and I'll share some example with you in a few minutes' time. So fixed design and fixed water demand. What we have found out also through this optimization, where we want to minimize the total seasonal operating cost, that you have got 4 seasons, roughly winter, spring, summer, and autumn. What should be the top brine temperature, optimum temperature, and what should be the brine level in the last stage of the process, and to minimize the total cost. And these are the optimum values here. And in process control terms, we have to track this temperature and level control. So we need both temperature control and level control to achieve the fixed water demand throughout the year. And that's what we have done a few years ago. Salih Al-Sadai was my PhD student from Libya, has gone back after finishing his PhD. So we will talk about this control as well. What did we do about this process control? Right. What and how to control? What we control, I have just mentioned that in different processes, depending on your objective, whether you want to minimize the batch time, you want to maximize your profitability, you want to maximize your productivity, you want to maximize the conversion, that you decide first, and then how to control, okay? So before we present the how to control, let's look at the control modes again very briefly. So obviously, you know, I'm not going to spend a lot of time because the time is short, I understand. You have got a proportional control. All of us know that. What is it? So it is a proportional to the error signal you have between the set point and your the measured value, and then you take that error and you apply through this equation here a proportional control. Integral control takes care of that error over the time, and then of course you have got 1 over tau I, which is the tuning parameter. And again, the control output is a function of integral of the error signal, which is defined here. So that's an integral control. The proportional integral control basically combines these two in this form, which is right at the bottom. So that's again a proportional integral control, the PI control we call it. Then it comes the derivative control, where it takes the derivative action of the error you have got. So it's showing the change of error with time. And then you use that information to design your control, and we call it derivative control. And PID control is basically includes everything, the proportional, integral, and derivative control. And you write it in this form, which is widely used in industries. I'm sure many of you probably have spoken this morning or whole day. Then in discrete form, the PID control at any point of time k based on the error in the time interval, previous time interval, and then you actually translate this equation into the discrete form here. And then you have got another control is on-off control. Of course, it's like a valve on or valve off, 100% on or 100% close or 100% open. So this is a like and on-off control. And of course, in many simple processes, which is not very critical and complex, simple on-off control is more than enough to do it. Okay, then comes the advanced process control. So in the advanced process control, I'm sure many of you have discussed that, and I'm not going to spend too much time. So you have got a model predictive control here. So basically, you take advantage of a very accurate process model. Look at this sort of figure here. You have got the model and you have got the actual process. And you take advantage of this to decide your control action. What happened is that this allows you to decide the future control action, for example, how you control. So look at here. So this is the prediction for future interval. So this allows you to predict that, to track your target temperature or target parameter, how you can predict the future control actions. And that model predictive control allows you to have that sort of facilities. Then you have got internal model control. Again, internal model control you can see here, and the model is used here, and you have got the process here, and this is slightly different than your conventional feedback control, where you can see the feedback control with the disturbance. I started with this diagram right at the beginning. It's a slightly different here, that your control actions, the manipulated parameter, not only goes to the process, but it goes to your model, and then of course that predicts what it should be. So there can be difference. You can have a plant model mismatch kind of thing, and that mismatch is used to drive the control action. So that's called internal model control, developed back in 80s by Manfred Morari and his group. Again, another advanced process control which we have been using for some time, which is known as generic model control, and the generic model control equations are very much like that. And as you can see here, so the first step here is to bring the process back to steady state here due to change in dy dt. And then, of course, the second expression here is introduced in order to make the process to have a zero offset here. So you can see here, if you can make it to zero, then of course you will not have offset. And we have been using it for some time. Barry Court and Sandy Maketo from Imperial College, they developed that. They use that control for batch reactor control. The advantage of that one, that you do not have to linearize your model equations. You can directly use your model equations into this control algorithm to find out your control actions, or to calculate or determine your control action. So generic model control has been used, originally developed by Lee and Sullivan in Toronto, University of Waterloo. I think they were, and Lee and Gary Sullivan, they were University of Waterloo back in 1988, and they developed this control system. And throughout the years, a lot of people use this generic model control for different processes. And we have used it also, our group with Professor Aslan, we have used process control or the generic model control quite a bit in our work. At this point, I think I have to thank Professor Aslan especially, that he actually hooked me to the world of process control, and especially neural network-based control. So I owe a great deal to him to get me interested in some of his work, and we continued collaboration over many, many years, and we published many papers. I think probably over 30 papers we published together in the past. Right. So now I go back to the examples where we applied the different control, and I'm sure is less time here. This is again from my PhD student, Malaysian PhD student back in 2001. You can see it's a simple, the first example, again, the example number corresponds to the same one. A producing B, B producing C, B is the desired product. So when we applied PID control, look at here, how, sluggish they are and how much oscillations there are, even though the offset at the end was small, but you can see the oscillation of the PID control. When you apply GMC control, taking advantage of the model equations directly, you can see how smooth these controls are. So GMC is less sluggish, and of course GMC does not require tuning of too many parameters, only K1 and K2 two parameters, while PID you may have 3 parameters to tune. So you can see this example that advanced model control, the GMC outperforms your PID, and nice and tidy picture. So example 2, where A plus B producing C, and A plus C producing G. So there's the paper we published together with Professor Aslan back in 2000, I believe, or 2001. So it has got a 3 controller actions, as you can see. We used PI, but it ended up with the offset, which is quite obvious. The PI control have got offset is not small. There will be some offset, even though it is small. But again, PI and PID, you can see PI more sluggish kind of thing, more oscillation here compared to PID. PID performed better than PI. But if you look at the GMC, again, very little oscillation here and tracking the reactor temperature very well for this particular. And this set point tracking temperature I have shown you right at the beginning when I was going through the example. So we are basically taking those temperatures and just tracking those. Next example, the polymerization of styrene. Again, third example. Set points I have highlighted in the past, and you can see here PID and GMC. We applied 2 of them here. Again, the GMC much better in terms of response, in terms of controlling the process or tracking the temperature. It could get to the steady state point very quickly compared to PID. And that's again a work we published back in 2007. There's again a polymerization of methacrylate we published in 2008, I believe, or 2009. Again, we applied only GMC control here, and just to show you, we were able to track the temperature, the optimum temperature we wanted to achieve. 5 example is a milk pasteurization process. Again, what we are trying to do, I'm just presenting 2 of the 4 controls we considered in that particular paper, worked with Thailand. So one is the boiler temperature setting and the ripple plate one. So boiler temperature has to be around kind of a 90-degree set point here. That's the GMC control. And this is the LPG feeding rate to produce give this certain amount of heating here. And there's the ice into the ripple plate here. And we were able to control that with the GMC here. But again, when we applied the model predictive control, that was better than our GMC. So if you look at the 2 figures, control response or MPC was less drastic compared to GMC action. So in this particular example, model predictive control works slightly better than GMC. Even if you look at the tracking of the ripple plate 1, it's very smooth, and down here as well. Right, so the next example is the desalination process. And the control variable, when you have got the top brine temperature, the manipulated variable, the steam flow in the brine heater here. The steam flow we are manipulating to control the top brine temperature. We have got 4 seasons, as you can see here. We obtained the optimum top brine temperature for season 1, season 2, season 3, season 4, and we applied the GMC control, and we are manipulating the brine steam flow rate. And as you can see here, the GMC tracked the temperature profile very, very well. And on the control output, you can see it's a scale 0 to 100. So either the valve was fully closed or fully open or in between kind of thing. So that was the manipulated variable here. And that is in desalination process. This is again the brine level. We have got a 4 brine level, as you can see here, for 4 seasons. And we applied GMC again by controlling the brine output flow. So from the last stage, that's where the brine outlet going on, the concentrated brine going back into the sea. And that was used to control the level of the brine we have got in this one, in this flash unit, the last stage of the process. And you can see again clearly the GMC was able to control the set point very, very well. And we published the paper in Journal of Process Control. Another example, we worked with Professor Aslan and Professor Naib Qasim from, he's in the United Arab Emirates here. Again, you can see that it is an industrial polyethylene fixed bed reactor, and the temperature control was considered here. And you can see the set points of the temperature at different time. And this is where we applied PID and GMC. I can clearly see the GMC control behaved much better and get to the steady state much quicker than the PID control. And that's on industrial reactor we had. Two more examples before I finish. I'm now introducing the neural network-based control, again, which we worked with Professor Azlan for some time with our PhD student. Two PhD students actually applied that. So one is the forward neural network model. What is here that you provide the past information of the temperature, the jacket temperature, as well as the reactor temperature, the past in a couple of intervals you choose, and then the heat of reaction kind of thing. You can see the heat, the amount of heat supplied in the past interval. So you predict the future reactor temperature in step k plus 1, considering all the past input at interval k and k minus 1 and k minus 2. Inverse neural network model is that you use some of the past one, but then again, you not only calculate the jacket temperature based on the past, but also based on the future set point you may have kind of thing. So yeah, if you know the future input of the set point you want to track, you can use that so that you can calculate that. So it's like an inverse neural network model. So direct inverse control here, where the neural network inverse model is used as a controller. So the neural network inverse model is actually supplying the UK, which is the control parameter here. And these are the neural network estimator for heat of generation, the heat of reaction sort of thing. And there's no feedback here. So you start with a value in the current level and your future state is being predicted here, no feedback control here. And then you have got the inverse model-based control with feedback. You can see a feedback here. So you have got a neural network-based forward model where the manipulative variable goes not only the way. So this part is like an internal model control I have presented here. And this one is working as a controller. So neural network itself, the inverse model acting as a controller kind of thing. So this is, again, the inverse model-based control with feedback. And one example we have given for this particular chemical reaction, which we have used. So you can see the GMC we have applied. I've shown that result just a few minutes ago. Then we applied both the direct inverse and the internal inverse model-based control, which is these two are neural network-based control. So we achieve very close results here. Even though looking at it, GMC looks like outperformed the other, but you have to remember the neural network-based controller, easy to implement, no tuning parameters, and easy to implement. And more future data you have got, you can have an adaptive neural network where you can train continuously on neural network as you need. So even though in this particular example, GMC was still better than the other, but implementation-wise, the neural network-based control, when you do not have do not know many of the physical parameters, the neural network-based input-output model can be very, very useful. So I'm nearly done. It's a 9:50, I believe, in UK, and I'm sure it's close to 5 o'clock in your place. So the next is my conclusion. Very simple conclusion. I have already mentioned number of these as I was presenting. So my conclusion is that not to control is not an option, because if you look at the productivity, quality control, and profitability, you cannot just sit back and let the process go without control. So not to control is not an option at all. You need to have the control. Now, the optimal control parameters must be identified, and the set point must be determined a priori. Either through the set of experiments in the lab, you determine what is the optimum temperature, what is the optimum flow rate, or you can use the model-based techniques to find out those optimal control parameters for the set point. Once you have got the set points known, then, of course, depending on the process, you have to choose the best control to apply. I have not discussed the robustness, the control robustness, the tuning parameters, how you tune. There's a lot of literature, but that was not the purpose of the presentation today. I just wanted to reiterate that not to control is not an option in every sphere of our life, and of course in that, and introduced you many controllers which we have been using over the years. So thank you again for listening to me. I was given 45 minutes. I believe I have used up that, and it's open to question now. Thank you.
Okay, thank you so much, Prof. Mujtaba. I believe your expertise and the knowledge you shared have enriched our understanding, especially on the revolution from the PID, GMC to the neural network-based control strategy. So I would like now to open the floor to questions from the audience. If you have any, you may unmute yourself or you can write in the chat box.
Dr. Huda.
Yes, Prof.
First of all, Assalamualaikum, Prof. Iqbal. I believe you remember me.
Yes, I remember you very well. Yes.
Yeah, for your audience information, Prof. Iqbal is my external examiner when I defend my thesis 19 years ago, Prof. 19 years ago.
Yes.
So thank you very much. Glad to meet you again, even though it's a virtual kind of environment. I think glad to meet you, in this kind of environment. And then I have one question regarding the process control, because nowadays, Prof, we're talking about the AI, the MLs, and recently we have quite a viral kind of a generative AI like ChatGPT, something like that. So, in your opinion, how we can infuse that kind of things in our process control kind of environments, in related to the facility that we have now as compared to 20 or 30 years back? I think that could be one of the reasons the generative AI comes to the picture. So how do we infuse that in the current kind of a situation for our process control kind of research kind of things, Prof?
Yeah, thank you, General. Nice to meet you and nice to see you. Unfortunately, probably you cannot see my face. Something happened with my camera or whatever.
Okay.
Or was my camera off? I'm not sure.
It's on, Prof. I can see your face.
Oh, you can see now. Okay.
Yeah,
good. Right. Okay, so I think the AI is coming with a great force. And I think 20, 30 years ago, when Professor Aslan was doing all his research in neural network-based control and etc., I think people did not realize at that point the value of those and the force that was coming with. And that was the reason in the last couple of slides I mentioned about neural network-based control, because that is the future. You can see that artificial intelligence, the neural network, the machine learning, that will, because implementation of those will be quicker, more and more data you get, you can adapt those to train your model or inverse control, at a speed we cannot even think of. And of course, that can replace many of the traditional control because they will perform better. So what I understand, that it is coming and it is the future. And of course, I have not done much work in generative AI kind of thing, but I'm sure some of you are doing that definitely.
In addition to that, Prof, I think because when we have looked at the fundamental of generative AI, for instance, like we have our model, right, developed by could be using the neural networks. So the best part in normal generative AI is they keep retrain the model with the new informations. Right? Yeah. They keep training. Sometimes as us, as a process control engineer, right, we don't want that to happen in some extent, because we don't want that the model keep retraining in the system, in the real time kind of environments, because that can promoting the turn down of that MPC and so on. What do you think about that, Prof?
You mean the continuous updating, continuous training?
Yeah, correct.
I think sometimes that can be a problem, isn't it? The overfitting and kind of thing. You may have some information which may not be. So data reconciliation, data filtering is essential. You cannot just train a neural network with anything it sees. So I think some kind of filtering mechanism should be there. Otherwise, you may end up with a wrong sort of heating kind of thing, because it is always an industrial problem, isn't it? Because you measure hundreds of data, but all data are not usable. So data reconciliation comes into the picture to conserve the mass and energy balance sort of thing. And with a continuous refitting or continuous adapting, that can be a danger also. So I believe some kind of filtering should be there, that which data you are using, even though you are doing in a continuous basis, that should be carefully thought about it, because otherwise you may be training your system with the wrong data, which may not be useful.
All right, I believe so means that we need to have kind of a tool or whatever mechanism that we can selectively choose what would say the quality kind of inputs or measurement to that system. Then in some measure we may avoid any retraining or remodeling that can disturb the process as well in some extent.
Yes, definitely.
Thank you again, Prof, for your opinions. I'm really glad to meet you again.
Thank you.
Thank
you very much.
Take care, Prof.
Thank you. Bye now.
Prof, there's another one question from Dr. Jobron in the chat box. I can read for you. Hello, Prof. Iqbal. Insightful. Yes.
Yeah, let me stop sharing and then I can probably go into the full mode and then, okay.
Okay.
Right, yes. Yeah, if you can do it, because I cannot see what is in the chat box.
It's okay, I can read for you, Prof.
Yeah.
Okay, this is from
please.
Dr. Jobron. Hello, Prof. Iqbal. Insightful presentation. There are many types of control techniques such as adaptive, fuzzy, GMC, optimal, and etc. Based on your experience, which of the types that are the easiest to apply and most efficient?
Sorry, can you read that question again? So I missed out the.
There are many types of control techniques such as adaptive, fuzzy, GMC, and etc. Based on your experience, Prof, which of the types that are the easiest to apply?
Yeah, I mean, we have used fuzzy controllers in the past and compared with GMC as well. It depends on the application where you want to apply. If I remember correctly, which we have used in desalination, the fuzzy control, I think it was with Professor Azlan as well in one of the conference papers we did. Fuzzy control performed very close to GMC. So again, it depends on the control techniques which you want to use, depends on the application, to be honest. In some cases, simple on-off control is more than enough when you are not too worried about the level of water or the liquid in a tank kind of thing, not going beyond the critical limit, but within the volume of the tank. Simple on and off is more than enough. So it depends on the application. In some applications, of course, they may be quite complex and kind of thing. Then what GMC offers is it directly can take into account the model, the dynamic model or the accurate model which you have. The other control systems, of course, that misses out those features of your process. So if you know your process very well, and if you can really accurately model your process and the thermophysical properties are known, then in my view, the GMC would be the best, because the GMC directly works with the process model.
Thanks a lot, Prof, for this for the keynote speech. We really appreciate the inputs and time you giving today. You are able to attend for this virtual symposium.